We mentioned that the key in the proof that length minimizing curves are geodesic is the first variation formula. The idea is that given a curve gamma, we can vary it in a family of curves with the same endpoints. Then if gamma is a length minimizing curve, then it, or shall I say its parameter, s equals to 0, must be a critical point of the arc length function on this family. Now, to show that in that case gamma must be a geodesic, we need to relate this derivative with the covariant derivative of the velocity vector field of gamma. From this being 0, we're gonna deduce that this covariant vector field is 0. And from this term here, we will deduce that gamma is smooth. So then gamma must be a geodesic. Now, to understand this formula, we need to introduce some new concepts to our discussion. In particular, we need to talk about vector fields along an admissible family. Given an admissible family gamma, as in this drawing, then a vector field along gamma is just a map from the same rectangle to Tm, i.e. the tangent bundle to M. It sends every point T0, S0 in this rectangle to a tangent vector at the point gamma T0, S0. This is a tangent vector to M at this image point. There are clearly two very special vector fields along an admissible family. The first one is the vector field along the main curves. For each fixed s, that would just be the velocity vector field of the curve gamma s. As s ranges over minus epsilon epsilon, we get this whole vector field along gamma, which we'll denote by either this notation or this, just for conciseness. Now, the other important vector field along gamma is the vector field along the transverse curve. And we will denote this by s of s, little t. And observe here, the length of the curve gamma s, by definition, if the curve is regular from A to B, then by definition this is just the integral of the speed of gamma s, i.e. the norm of the length of the velocity vector field of gamma s, which is just this vector field that we just mentioned. And that is how we will start this proof. But before moving on with the proof, let us explain the last terminology. We want to define the notion of a variation field of this big gamma in the case when this big gamma is a variation of some curve, little gamma. Remember, this means that every element in this family, big gamma, has the same starting point and end point as this little gamma. Now, this variation field of this big gamma is gonna be a vector field along the curve little gamma. Remember, gamma, in a variation gamma, is gonna be the curve corresponding to s equals to 0, right? So this is gamma, big gamma 0 t, whereas we view each curve in the family as gamma s of t. The variation field captures how this little gamma varies as we vary the s. Formally, it's defined to be the partial derivative of this family gamma in the direction of s and evaluated at 0, t, so along this curve. And in terms of our previous notation here, this is just s of 0, t. So it's the part of this vector field in the transverse direction, but restricted to the curve gamma. And unsurprisingly, the change in this arc length as we go over curves in this family can be captured in terms of this variation field. In the next video, we're gonna explain the intuition behind this first variation formula and give the proof.